magnetic wave equation, we also need boundary conditions for these wave equations and for the electromagnetic fields. So the boundary conditions are derived from the Maxwell equations. So let's look at an electric field or electromagnetic wave that's propagating from medium 1 with these parameters for the magnetic susceptibility and the permittivity and the magnetic susceptibility, going to another medium with epsilon 2 mu 2. We can apply that the first boundary condition we can derive using the Maxwell equation for the curl of E, gives us that, and I'm not going to go through the details, you can look at this in any electromagnetic textbook, that the tangential component of the electric field must be continuous. So by applying it across a loop, across the interface, we can show that the tangential component of the electric field must be continuous at this interface. Similarly, we can apply for the magnetic field, and there the magnetic field also, as you see here, this is the tangential component of the magnetic field, ends up being continuous across the interface as well. So those two equations, except in the case when there is a surface current, such as at the surface of a perfect conductor. But if you're considering dielectric materials where no currents are flowing on the surface, then this right-hand side will be 0, and therefore the tangential component of H will also be continuous. We can also apply this to the normal components using Gauss's law, and that gives us that the normal components of the electric flux density is continuous, except when there might be a surface charge. And such surface charges can exist at the surface of a metal or the interface between two dielectrics. And the normal component of the magnetic flux density B ends up being continuous, and this is because the corresponding Gauss's law, because there are no magnetic monopoles, del dot B is 0. That gives us that the normal component of the flux density is continuous across interfaces. Finally, we can also incorporate the continuity equation, which says that charge conservation takes place across any interface, and by again applying a integral version of that across some little pillbox structure across two interfaces, we can show that the normal component of the electric current density is continuous, again, except wherever there might be a time varying surface charge, such as at the surface of a perfect conductor or the interface between two dielectrics. So all of this is now summarized in this slide. This shows you all the various structures that we used, I mean little surfaces and loops that are used to derive these various conditions, and which can be written down over here. And we use various theorems from vector calculus. I just summarize them here, which in case you're not familiar, you can use these, but I recommend you just go and read a textbook on electromagnetism for this part. Okay, so with that, let us now consider what happens in the S polarization case. I'll just illustrate the what is going on, and we're going to see from this how we can get the Fresnel coefficients or the coefficients for the reflection of this S polarized light. So we apply the first boundary condition, that is that the tangential component of the electric field is continuous at this interface. So I've drawn again the same conditions. So I've used EI and BI to represent the incident field, ER and BR to represent the reflected field, and ET and BT to represent the transmitted field. Okay, and since all the fields and the axes that I'm choosing is that the z-axis is perpendicular to the screen, that is along the S polarized field vector, and the various other axes are shown there, X and Y. We see that the Y equal to 0 plane is the X-axis, and that is the plane of incidence or the interface. Is the plane of the interface, not the plane of incidence. The plane of incidence is the XZ plane in this case. Okay. We are not explicitly going to write all the X, Z, and T dependence. We only care about the amplitude right at the interface. but of course all those dependencies are also there. Since the component of the field that lies in the XZ plane, that is the plane of the interface, which is tangential to the interface, is continuous as you move across the plane of interface, we can immediately write down that the EI, which is the E fields, are all in the Z direction, and which is in the plane of the interface, and therefore the sum of the E components along the Z direction before the interface, just before Y equal to 0, that is EI plus ER, must be equal to the transmitted field ET at Y equal to 0. Similarly, we can do the same thing for the tangential component of the magnetic field, because remember that was one of the boundary conditions that we discussed in the last, in one of the earlier parts of the lecture. And now we have to be a little bit more careful. We have to take into account that the B field, which is pointing in this direction, it's a tangential component to the interface. That is a component along the x-axis now, which is along the interface. It's tangential to the interface. That component is going to have a negative sign, right? So if BI was the magnitude of the field, then it's minus BI cosine theta I is the part that's tangential to the interface. Similarly, BR plus BR cosine theta R is also tangential to the interface. So those two will add together. And according to our sign convention, X was shown to be positive along this axis, along this direction pointing to the right, and the other direction, which is minus BT cosine theta T, that is also negative in this direction. And of course, really it's H that is continuous, but we can, that is just B over mu, and since mu is always chosen to be mu naught, we are not looking at magnetic fields, therefore we can just neglect the magnetic permeability in vacuum and get this expression. So, and with those two equations and the fact that B, which is equal to E divided by the velocity of the light in the medium, so that is just simply B is equal to E divided by C naught over N, or E divided by the C over N, where C naught just represents C, the speed of light in vacuum. So we get B is equal to N times E divided by C. And of course, we have the law of reflection, theta I equals theta R. We can actually derive it from these expressions, but we're not going to do that. Once we put in the KZ dependence, it'll come out, but we're not going to do that here. And then when you substitute the equations for E, for B into that expression for B cosine theta and B cosine theta R, and then substitute for E naught of T using E naught I plus E naught R equals E naught T, that eliminates the transmitted beam, and we get purely the reflected terms over here. And now we have everything in terms of reflected field and incident field, so we can solve for the reflected field in terms of the incident field and these various angles. So that gives us this expression. This is the first Fresnel coefficient for R perpendicular. I wrote perpendicular, but it's the same as RS, which is the S-polarized light. And R perpendicular or S-polarized RS is simply this formula Ni cosine theta I minus Ni cosine theta T plus and divided by this formula. Similarly, we could have solved for the transmission coefficient. That gives us this expression. These are the Fresnel equations for perpendicular polarized or S-polarized light. We can similarly do the same sort of analysis for the parallel polarized light. I'm not going to do it. And we'll get some expressions. These expressions are given in your textbook. For our purposes, all we really need to know is that they form this sort of interesting combination, which you can see here. So I've sketched the values that you can get from your from the equations in your textbook. You can get RS and RP. And from that, we find that there is a particular angle, at which this R parallel, the parallel component of light vanishes. That is,